This video will be covering section 3.1, extrema on an interval. So when we talk about the word extrema, that is a plural word for extreme. So we're talking about extreme values on an interval. So basically what we're talking about is the highest or lowest values on an interval. So with that, we're going to introduce the extreme value theorem. So remember, a theorem is going to be an if-then statement. So if we know the conditions are to be true, then we can assume the following. So if we know that f is continuous, which means informally that there are no jumps or holes on the interval from a to b. And it's important to note here that the interval from a to b is a closed interval. That's very important. It's not an open interval. It has to be a closed interval. That means the function is defined at both a and at b. So if we know that, then we know for a fact that f has both a minimum and a maximum on that interval. And together, a minimum and the maximum are called our extrema. Oh, not estrema, extrema. So the extrema, if I ask you to find those, would be to find the most minimum point and the most maximum point on that interval. Okay, so let's look at this first example. Consider this graph on the interval from the closed interval from 0 to 8. So here at 0 and here to 8, we first want to make sure that it is continuous on this closed interval. And yes, it is continuous. There are no holes or jumps or asymptotes or anything on this interval. So we can apply the extreme value theorem. Therefore, we know that there is both an absolute maximum and an absolute minimum. So another way of saying extrema, if I just said the maximum or the minimum, then we assume that that's the absolute. But another way of saying it, just to be clear, is absolute maximum or absolute minimum. So the absolute maximum, and it's important here to know your English very well, the absolute maximum is the y value. And then it occurs at the x value. So if I were to say f has an absolute maximum of, we're asking basically like what is the height, what is the y value. So on this interval from 0 to 8, the highest value occurs at 8, but the absolute maximum is 5. So f has an absolute maximum of 5 at the position 8. So it's very important that you do not say it has an absolute maximum of 8. The absolute maximum is not 8, it is 5. So then the absolute minimum of this graph occurs here, and so the absolute minimum is 2, and it occurs at 5. Okay, so in addition to absolute maximum and minimum, so that's absolute max and min, we're talking about extrema, so that's the extreme value theorem. So we know, again, if f is continuous on a closed interval, it has both. If it's not a closed interval or if it's not continuous, we cannot say that. So we also have other maxes and mins, and those are called relative or local max and mins. So in addition to absolute, we can have relative. That's kind of like, let's say in Texas, the highest point in Texas is Guadalupe Peak, and that would be the local maximum of Texas. However, is that the absolute maximum on the planet Earth? No, that's Mount Everest. Mount Everest is the absolute maximum. But Guadalupe Peak is still a local maximum. In relative to the area that it's in, it's still a maximum. So we also want to be concerned with relative maximums. So for instance, f has a relative maximum. Also here, it's not the absolute maximum, but around that area, if you close into that area, it looks like a maximum. So it's also a maximum, but not absolute. So that's a relative maximum of 4, and it occurs at 2. F has also a local minimum, and it doesn't have any other minimums besides, we can't really say anything about 3. You do not have relative or local minimums at endpoints. You can have absolute maximums at endpoints, but not local. So the only local minimum is the same as our absolute minimum, which is 2, which occurs at 5. Okay, so as I already said, remember the relative extrema are the hills and valleys. So within any given interval, you have lots of hills and valleys, but the absolute extrema are the highest and lowest points. So you only have one absolute extrema and one, or maximum, and one absolute minimum. Okay, so then the value of the derivative, since we're talking about derivatives, the value of a derivative at a local max or min must be, so if you look here, we have two places that are not at endpoints, here and here. So if you think about the derivative or the rate of change or the slope of the tangent line, what is the slope of these values? Well, at this one here, if you took the tangent line, the slope of that tangent line is 0. This tangent line over here, so that's a slope of 0. This tangent line here, it's a cusp. So you cannot have a derivative at a cusp. The derivative there is undefined. Okay, so relative local max and mins can occur either at when the derivative is 0 or undefined. A lot of people remember 0, but they forget undefined, so that's something to remember. But remember that it can be undefined, but your function still has to be continuous. So a cusp, which is something like this, so a sharp point, that's called a cusp, is where we have differentiability. Sorry. We have continuity, but not differentiability. So that's important to remember. Okay, we just said that the value of a derivative at a local min or max has to be 0 or undefined. But is the converse of that statement true? That is, if I have a derivative of 0 or undefined, does that mean that there is a local min or max? That is not necessarily true. Okay, and we're going to look more into that in the upcoming days, but just know that just because you have a 0 or undefined derivative, it does not necessarily mean that you have a min or max. Okay, but if you do have a derivative of 0 or undefined, then we do have something that we define here, and that is a critical number. Okay, so as long as f is defined at c, and that's an important information, as long as our original function exists at c, then if f prime of c is 0, or f is not differentiable, that means f prime is undefined. Then c is a critical number of f. Okay, so we have critical numbers, and then those critical numbers may or may not be mins or maxes. Okay, so an absolute, and again, this is an absolute min or max, must occur either at a relative min or max, or, as we saw in the very first example, we can occur at a relative min or max, which is here, these two places, or our absolute max in this example was at an endpoint. So when we talk about absolute max or mins, we're going to not only look at the relative mins and maxes, but also endpoints. So that's very, very important. These definitions are very, very important, something that you're going to need to memorize. All right, so now how do we find absolute extrema? When we did our first example, it was very easy. We have a graph, it's very easy to see. But what if we don't have a graph and we're not allowed to use our graphing calculator? How do we find the absolute extrema? And actually, we need to show our work to prove that those are the absolute extrema. So we have this, which is called the candidates test. So a candidate is something that could be an absolute extrema. So we're going to find candidates and test them and see if they're absolute extrema or not. Okay, so the first step is to find the critical numbers of f. Remember, our definition said a critical number is where the derivative is equal to 0 or undefined. So we're first going to take the derivative of g. So the derivative of g is 3x squared minus 12. We want to find when that is 0 or undefined. This is a quadratic. It's not undefined anywhere, so we're only concerned when it's equal to 0. But other functions you want to check to see when it's undefined, like a square root or a fraction or something like that. So 3x squared equals 12, so therefore x squared equals 4. So x equals either plus or minus 2. Okay, so those would be critical numbers. So that's our first step. Now, be careful here, though. It says find the absolute extrema on the interval from 0 to 4. And you see here that -2 is not in my interval. So therefore, positive 2 is our only critical number. So -2, not an interval, means I don't need to look at that one. I only look at positive 2. So positive 2 is my only critical number for this interval. So the second step is to evaluate each critical number in the interval from A to B. Now I'm going to combine 2 and 3. I do these at the same step. So it says to evaluate each critical number. We found it to be 2, and each endpoint. So that means both A and B. So here it's 0 and 4. I like to do a chart here, so I'm going to make a XY chart. So we have x and we have g of x. Now we're not concerned with the derivative anymore. We're looking at the values of g. So we're looking at when x is 0, that's the first endpoint. In between is 2, that's our critical number, and 4 is our other endpoint. And I'm going to evaluate g of x. G of x is x cubed minus 12x. So at 0, we just have 0. At 2, that's 2 cubed minus 12 times 2, or 8 minus 24, which is negative 16. And when we evaluate at 4, we have 4 cubed minus 12 times 4, which is 64 minus 48, which is positive 16. Okay, so then that's steps 2 and 3. So then the last step is the least of these values is an absolute min, and the greatest is the absolute max. So we just identify those. So the smallest value is negative 16, so that's our absolute min, and the biggest value is positive 16, that's our absolute max. Just a word on notation here. We're not done. Yes, we've identified the min and max. However, you need to put your answer in a complete sentence. That is very, very important, and you need to prove using the right vocabulary. So that's something very important with calculus that I'm teaching you now. So to wrap all of this up and to get full points for this problem, we would go back and kind of restate the problem. They want to know the absolute extrema for the function g. So we want to have a complete thought here. So we're going to say, okay, what function are we talking about? We're talking about g. And it has an absolute min of negative 16 at x equals 2. So you want to phrase it very, very specifically. Then you want to say g has an absolute max of positive 16 at x equals 4. This would be our final answer.